Hi, this is a video to help you through the activity on percents and significant figures. To do this activity, you'll need a little pack of M&Ms, and I'm going to tell you that this pack is about 15 grams. Before we start, I'd like to say in the first part of the activity, I'm not going to focus on significant figures at all. I'm just going to focus on percents. So to start, we're going to predict the total number of M&Ms that are in this pack, and we're also going to predict the green and orange M&Ms. Your answers might not be the same as mine, but here are my predictions. The predicted values here are going to serve just like literature values or theoretical values. They're our guesses or educated guess, and they are what we would expect based on previous experience. Now we're going to calculate the predicted mass of each M&M using our predicted values and the fact that each package has approximately 15 grams of M&Ms. So to calculate the predicted mass of each M&M, you just take the total package's mass divided by the number of M&Ms you predicted. In my case, I would get 1.5 grams per M&M, and I would put that in the box. And now I'm going to predict the percentage of green M&Ms in grams. In the next box, we're going to predict the percentage of green M&Ms in grams and the percentage of orange M&Ms in grams. A percent is a part divided by a whole. And in this case, we're going to take the part of green or orange M&Ms in grams and divide it by the whole mass of the package and multiply by 100%. Here's the math that I would use, or the formula I would use for the green M&Ms. I need to find the grams of the package that are due just to the green M&Ms and divide it by the mass of the total package in grams. So to find the mass of the green M&Ms, I'm going to use my predicted number of green M&Ms here multiplied by the mass per M&M. So on the top of this equation, I would get an answer that would give me the mass of green M&Ms in this package. And then I'll divide it by the mass of the total package and multiply by 100 to get a percent. And in this case, I get 30% green M&Ms. I would do the same thing with the orange. I need the number of grams that are due to the orange M&Ms, and then I can divide by the total package and multiply by 100%. Here I guessed 2 orange M&Ms. I'll multiply it by the mass of each M&M that I predicted, and then I divide by the total grams of the package, and I get 20% orange M&Ms. So these are my predicted values. Remember that these would be similar to a theoretical or a literature value. They're what I would expect, but not my actual data. My predicted values are now in the purple box. And the next thing is to calculate my actual values. So I'm going to now open my package of M&Ms and put my actual values, or do my actual calculations, and fill it into this next box. My actual number of M&Ms in my package was 18. And I still have the number 15 grams because I know that the mass of the package is approximately 15 grams from the larger bag that I bought at the store. So when I divide the mass of the package by the actual number of M&Ms, I get my actual mass per M&M, and it's shown here in this box. I actually had 5 green M&Ms, and I actually had 3 orange M&Ms. So now I can calculate the percentage of green in grams and the percentage of orange in grams using the same process that I used for the predicted values. So I take the number of green M&Ms I found times the actual mass per M&M divided by the total grams of the package, and I get approximately 28% green. And then I will do the same thing for the orange. And then for the orange, I get approximately 17%. Remember, at this point, I'm not worried about significant figures. I'm just doing some calculations. Percent error is a really important thing to know about, especially for our laboratory. Percent error is the difference between the actual value and the predicted value. And I've written this in absolute value bars on this equation because it's really, what you're doing here is you're taking the part that is different from the actual value, or the difference between the actual and the predicted values, and dividing it by the whole actual value, multiplying by 100%. So it really doesn't matter if you take predicted minus actual or actual minus predicted, as long as you know what the difference in these two values are. So if I want to predict the percent error in green, there's a couple different ways I could do this. It's not specific on this chart, so I could use my percent error in green according to the number of M&Ms, according to the mass of the green M&Ms that I predicted versus the actual, or I could do the percent of green versus the predicted percent of green versus the actual percent of green. So it's up to you, but I'm going to be simple and I'm going to use the actual number of M&Ms. So my actual value was 5 M&Ms, 5 green M&Ms here. And I want to subtract the predicted number of M&Ms and divide by the actual number of M&Ms. And then I can see here that I get 40% error in green. And if I do the same thing with the orange M&Ms, take my predicted value and subtract it from my actual value and then divide by the actual value, I get around 33% error. And error in the grams per M&M, now I'm being pretty specific, so I want to compare the mass per M&M that I predicted to the mass per M&M that I actually got. And here's the math that I would use to calculate that. So I get approximately 80% error in the mass per M&M. Okay, so this is how we do percents. All of these percents are a part divided by a whole times 100%. Percent is always defined per 100 units, or 100%. So always multiply by 100 if you're looking for a percent. Now we're going to talk about significant figures. And before we do that, I want to talk about the difference between precision and accuracy. A really nice way to talk about precision and accuracy is to keep this mental picture in your mind of the targets that are on this page. At the very bottom left-hand corner here, I have a target where I have 4 shots, or I'm going to call these data points. These 4 data points are very close to the bullseye, the thing that I was aiming for. And that means that I was very accurate. The shots, or the data points, are also very close to each other, which means that they're precise. When we're talking about accuracy, we're talking about how close something is to the bullseye, or how close is it to our predicted value. Precision means how close are the data points to each other. If we look at the target that's on the lower right-hand side, we see that there are 4 data points here that are very close to each other, but they're not very close to the bullseye. This is an example where something, or a group of data points might be very precise, but not very accurate. So they're very close to each other in value, but not very close to the real value, or the predicted value where we were trying to aim. Here's another example of something where it's very accurate, but not very precise. If we took the average of these shots, or these data points, you would get something very close to the bullseye, which would mean that your data was very accurate. However, the data points are not very precise because they're all over the place. They're not close to each other. And you can also have something that's not very accurate or very precise. When we are in lab or in a medical situation, we want to shoot for both accuracy and precision, but we can discuss them independently of one another. So keep these things in mind as we go through our labs and as we talk about significant figures, because significant figures can tell us something about how accurate and precise some measurement is, or a dosing recommendation is. So here are the general rules. In general, anytime you have a digit that is not a 0, it will always be significant. So here's an example. These are all non-zero digits in 12.4, and that means that all of these digits are significant. So since there are 3 digits, there are 3 significant digits or 3 significant figures. Zeros are the things that sometimes count and sometimes don't count. And the next 3 rules here are going to be pertaining to the zeros. So zeros that are between other digits are always significant. So here's an example. These 2 zeros are between these 2 other digits. And since the 1 and the 2 are significant and the zeros are significant, then we have 4 significant figures in this 100.2. Leading zeros are the ones that are to the left-hand side. So here's an example. These leading zeros are what we're talking about, and they are never ever going to be significant, no matter what. Leading zeros to the left hand of any non-zero digit are never significant. So this number only has 2 significant figures from the 9 and the 3. Trailing zeros, on the other hand, are significant sometimes and not significant in other times. So the rule is that trailing zeros are the ones that are to the right. So we're talking about this one, these 2, this one, and these 4. They're all to the right of the non-zero digits. So these things are only significant if there's a decimal. So in this number, there's a decimal. That means that this 0 is significant. There's a decimal here. That means that both of these numbers are significant. Decimal, yes, it's significant. No decimal, that means there's only 1 significant figure in this number, 60. And once again, no decimal, only 1 significant figure from the 4. So these are the general rules if you're given a number. And you'll need to remember these rules as you're doing mathematical manipulations. The rules are different depending what mathematical operation you're doing. First, let's talk about significant figures during multiplication or division. When you're multiplying or dividing any numbers, the number of significant figures in your answer must be equal to the smallest number of significant figures in the original operands. Operands is just a fancy name for numbers. So here are our operands, and you're basically going to be limited in your answer by the operand that has the least number of significant figures. And this is the case when you're multiplying or dividing. So here we have 3 significant figures, 2 significant figures, and 3 significant figures. So since the operand with the least number of significant figures has 2 significant figures, then we must round our answer to 2 significant figures. So the correct answer for this problem would be 2.2. When you're multiplying and dividing, you want to focus on the total number of significant figures in your operand, and your answer is limited by the operand with the least number of significant figures. The rules are different when you're adding and subtracting. When adding and subtracting numbers, you're now focusing on the number of decimal places, not the total number of significant figures, but just the number of decimal places. And your decimal places in your answer are going to be limited by the least number of decimal places in your operands. So here's an example. We're adding these 2 numbers. In the first operand, there are 3 decimal places, and in the second operand, there are only 2 decimal places. Our answer is going to be limited by this number, which has only 2 decimal places. And so when we round our calculator answer, we need to have 2 decimal places to the right-hand side of the decimal. It's a good idea to keep these rules in mind when you're doing all your mathematical manipulations in this class. From now on, we're going to expect you to report your answers in the correct number of significant figures. This can be particularly challenging if you're doing both of these types of operations in the same problem. So you have to keep track of both types when this happens. And here's an example. Here's a problem where you're calculating a percent, and in a first step you have to subtract, and in a second step you have to divide. So you need to keep track of both sets of rules for significant figures. In the first operation, I would subtract 0.250 with 0.208. And here is my calculator answer, 0.042. In the second step, I would divide 0.042 by 0.250, and this is my calculator answer. And then if I multiply that by 100, I would get this as my calculator answer. I wrote out all of these steps so that I could show you how you would tackle something like this. So in the first step here, when you subtract, now you need to pay attention to the number of decimal places. So the answer on the top of this equation here would be limited to 3 decimal places because there were 3 decimal places in both of the numbers that you subtracted. So here you'd be limited to 3 decimal places, and this is written as you would write it. And notice now that you have only 2 significant figures in this number. So when you divide this number by this number, now you are technically limited to 2 significant figures in this number because of that 0.042. The 100% does not limit you because this is an exact number. When you're working with exact numbers, you can ignore them as you're figuring your significant figures. But because I was limited to 2 significant figures here, I would round my answer to 2 significant figures, and the final correct answer for this would be 17%. It's a good idea to work through your entire problem without rounding and then go back and mentally keep track of the significant figures or the number of decimals in each step. Sometimes it's very good, though, to write out each step so that you can keep track of it in this way that I've shown you. So now, if we go back and look at the number of significant figures we wrote for some of our answers, we might want to change them. So further on in your activity is a blank table where you can rewrite your answers in the correct number of significant figures. I would like to point out that all of the numbers of M&Ms that I guessed or that I actually got are exact numbers. For example, I knew that there were exactly 18 M&Ms in my package, and I know that there are exactly 5 green and exactly 3 orange. There's no uncertainty here. So these are exact numbers. And the only number on this whole slide that would limit us is the number of grams per package, because this is an approximate number. It's not exact. So all of the calculations that involve 15 grams per package would be limited by this number. And so I actually end up with the calculated values here. Most of the calculated values are going to be limited by this number, and I end up with 2 significant figures for my actual mass of the M&Ms, 2 significant figures for these guys, and then all of these also ended up being 2 significant figures for my calculations. Yours might be different. For my percent error in green M&Ms and orange M&Ms, I use the number of M&Ms to calculate these. Since the number of M&Ms is an exact number, the number of significant figures in this answer are unlimited. And there's not a really good way to show this, and so I'm going to show it here by just saying exactly 40% error in green and exactly 33% error in orange. My percent error in grams, however, is not, or it was limited by this 15 grams. And because I was doing a mathematical operation involving subtraction and then division, I ended up with 1 significant figure in the end. Yours is probably 1 significant figure, but it might be different. At the end of this activity, there are some more practice problems to help you really solidify your understanding of significant figures and percents. So please do those questions and ask me if you need any help. Remember that the key is available on Blackboard.